demo lab. So the plan is today that I will give first a brief presentation about what demo we are going to show here about the nano diamonds. And the demo experimental part, Priya Yadav, she is a PhD student, third year PhD student. So she will show you the demo. She will also participate with me in the demo. So the idea is that as we have learned that NV exhibits fluorescence. So we have here a very basic setup to measure the fluorescence starting from scratch. So we will demonstrate various things. The idea is that first we will show you the basic experimental preparation. So that is actually the setup here. And then how do we make NV sample? So we actually purchase the colloidal solution of nanodiamonds and then we put them on slide. Then we will describe the setup. So it is basically a custom made microscope setup. You can see everything is like assembled here and we can change various parts and we will explain you all the parts one by one. Especially what are the lasers, optics, what are different detectors, spectrometer, and also the microwave excitation. The microwave part we will not be able to demonstrate right now, but I'm just showing it as a part of the setup. And after describing the setup, we will make certain observations with you step by step, looking at the NV sample slide, then exciting them with laser, then the fluorescence, then capturing the spectrum. So we will go up to that part. And finally, I will discuss some components of the ODMR, but the setup is not yet ready for ODMR detection. So after this demo, we will try and hopefully we can show you next time. Okay, so the sample preparation starts with a commercial colloidal solution, and maybe I will just give a brief overview, then you can demonstrate them, how do we do. So the specifications from the manufacturers are that this solution has 120 nanometer diameter nanoparticles on an average, and typically it is 1 milligram in 1 milliliter of deionized water. And the concentration of nitrogen vacancy is 3 ppm, okay? So 3 part per million. And then what we do, we start with the drop casting that solution on a cover slip, and we can spin it to make a uniform, like almost uniform deposit, or we can leave it as it is for some crude observations. And you can see in the picture on the right, this is actually the nano diamond deposited on ultra thin glass. So ultra thin glass is 30 micron thin glass, which is now available in our foldable devices, right? So you can see that, and for this picture we took the glass and then cut with the laser. So you can see the side view. So side view is like that, and you can see the glass thickness is 30 micron, and on top there is some white layer, nano diamond layer, which is about a few micron thickness. And how do we know that the solution we have is actually nano diamond? So we also do some basic structural characterization. For example, one can do the transmission electron microscopy. So if you know about the TEM, then it is like we have a TEM grid, and then you take the nano diamond, deposit, and then put it under the transmission electron microscope. And there one can see that we can zoom in and one can see the lattice spacing, right, 2.06 angstrom. So these are actually a proof that there are some crystals inside. The resolution of TEM, however, is not enough to actually measure the vacancy, right? And also the TEM will just show you the two-dimensional picture of the nano sample, right? But it's showing that we have the nano diamond crystals. And we can also do the XRD, and you can see the XRD, we have a very specific peak at 111 location, right? So this actually proves that there are nano diamonds in the sample. In addition to this, we can also do supplementary measurements like Raman or FTIR, right? Okay, so this is the basic setup, and there are different components in the setup. So that actually she will explain. So, and the basic idea is that we will excite the samples with a green laser, as Professor Rock told, that and we absorb in green and then it emits in the red fluorescence. So we will then capture the fluorescence and measure the spectrum. This is a typical image of one NV center, uh, not single NV center, but one spot on the on the on the sample, right, excited by the laser. We will see these images live, and these are the spectra, and we will also try to measure the spectrum, and you can see there are very specific the zero phonon lines, NV0 at 585, then we have zero phonon line for NV minus 1, and these are three different spectra for three different laser powers. As we increase the excitation power from 6 microwatt to 10 microwatt and then 20 microwatt, right, you see the fluorescence is increasing, obviously, because now more and more photons are exciting the NV. And we are way below the bleaching threshold. So if we reach the bleaching threshold, then of course everything will collapse. This is another experimental parameter that we can tune, because in the spectrometer we also have a possibility of acquisition time. So you keep the power fixed and change the acquisition time. So that also improves the spectral collection, and it also shows that the counts increase with more exposure time. Okay, this is some cross check, because as we see, the defects are very common in most of the systems. So we put the NV on the glass slide, and how do we know that the observations we are making is not because of the defects present inside the glass, right? So for that, this was the question asked by us from the referee. So for that, what we do, we take the glass and observe the fluorescence without NV, the left side picture, and you can see the laser power is 5,000 microwatt, so it's about 5 milliwatt power, and we see very little counts of NV, like 20, 25 counts from the background. And in this work, we also cut the glass with the femtosecond pulse. So there is also possibility that the femtosecond pulse can also induce some defects in the glass, right? So that we see some signal, but it is very weak. And on the same slide, if we deposit NV and capture the fluorescence, then you can see the counts are huge, right, 1800. So even though there may be some background counts, but they are very little. So whatever we are observing is mostly because of the NV center. Okay, so this is actually up to this point we will like to show, and this is the ODMR signal that Professor Rock showed. So this we captured in the setup, and you can see we have the excited state ODMR at about 1.4 gigahertz, the left peak, the small amplitude dip, and on the right we see the main 2.88 gigahertz ODMR signal, right? And there is also some splitting of about 30 megahertz, which is because of the residual stress, because how they make these nanoparticles are that they grow the diamond and then they crush it in the milling. So some stress is left behind, and that actually splits the ODMR line. These are of course supplementary measurements of ODMR at different excitation power. So the idea is that we vary all the parameters and try to make sure that the observation we are doing is consistent and is coming from the sample of interest, not from any other background. And all the pattern in the experiment, that trends, etc., they follow our expectations about the behavior of the sample, right? So that is the idea of varying different parameters and cross-checking and so on. Okay, so now I will request Priya to demonstrate you the experimental procedure.
Now you guys can come forward maybe. Okay. So
Start with the sample.
yeah. To make sample, here we have a glass slide, and this is the solution of nano diamonds. We simply simply take this solution and drop cast it on a glass slide, you can see. Okay. Then we let it to dry maybe for 3 to 4 hours. Yes, and we already prepared the slide with a dry state, so you can come forward if you want to. So this is our fluorescence microscope setup, and as Professor Roque told that to excite NV we use green laser. So here we have a green laser which emits a wavelength of 532 nanometer. Then this light passes through a ND filter which basically controls the intensity or power of the laser light which reaching at the sample. Then this we have a chopper which acts as a on off switch for the laser light. After that this passes through a iris, and this we use to check the alignment of the laser beam. Then this passes through this periscope assembly, and it is used to increase the height of the beam. And after passing this periscope, we have another iris to check the alignment of the beam. After this iris, it reaches on this dichroic mirror. This is the dichroic mirror which reflects this green light towards this 40x objective, and this collects this light on the NV sample. This objective lens has a numerical aperture of 0.6, so basically it focuses on a very small spot on the sample, and the emitted fluorescence then travels back to the same objective and passes through this dichroic mirror and then falls on this notch filter. This is a notch filter, we can adjust it accordingly, and this blocks the 532 nanometer and allow to pass the fluorescence which is emitted by this sample, which is I will show you. So after that, this is a beam splitter, and it split the fluorescence light into two paths. One goes to the camera for imaging, and other one goes to the this spectrometer probe. This collects the spectrum of this beam. So to show the spectra first, can we switch off the light for some time? You can see these are the nano diamonds. Okay, and yeah, okay, and this is the fluorescence light, you can see. Aage, this is the okay, this is the fluorescence light, and if we want these patches, these are the clusters of NB. So if we want to collect the spectra from here, then here we have a software of that spectrometer which we are using, and we simply on the take signal. So in this case, this is the spectra in a case where laser light and white light both are on. So now if we want to count only the fluorescence spectra, then we have to switch off the white light, and now we can collect the signal. So this is the fluorescence spectra of NV, and here we can see that here around 580 we have a bump, and which shows the NV0, and at 637 or 640 also we have a bump which is for NV minus for the sample. If
the power? Did you show the
yeah,
power?
yeah, I can measure. So, yeah. To white light is only used to see the NV. Otherwise, there is
So
no use
what?
of white light in fluorescence measurement. So, okay.
So what we will try to do, that we will try to measure the power of the excitation and the fluorescence
Yeah.
at different parts of the setup, right? So this is, can you describe what is this device?
This is a
Good camera.
Acha. This is a power meter which works between 0.5, which can measure power between 0.5 milliwatt to 50 milliwatt. Okay. So,
This is that is the maximum range, but it can measure up to nanowatts. So it is a
yeah,
very
and minimum.
sensitive power meter. Okay.
So, if we measure
And you
the,
can directly read the power here, right? Yeah.
if we want to measure the input power, which comes from the laser, so here it is, sir.
So input power is about 70 milliwatt, which is a bit too much, right?
Okay,
So I think you can
and
maybe
after,
attenuate it. Okay, anyway, doesn't matter.
okay, after passing through this iris, it is, how much it is?
65 milliwatt.
Okay, and to, after that, if we want to measure after the
Measure
dichroic mirror,
before the mirror.
dichroic mirror, okay.
Yeah.
So here it is.
So 59 milliwatt. So the
Okay.
power is reducing because every mirror is losing some power. Then how much it is entering in the objective?
Yeah, we can measure it from here. It is
13, 14 milliwatt power, right?
13
Entering in the
milliwatt.
objective.
Okay. Okay.
We don't want to measure, I mean, we can measure in principle, but let us say the worst case scenario, the objective absorbs 50%.
Yeah.
So it would be about 7 milliwatt going onto the sample,
Sample. Yeah.
right?
Yeah.
Now, a part of it will be de-emitted. So how much is that, the fluorescence light?
Yeah. Okay. So I will show you. Yeah, it is.
0.2
Micro.
microwatt. 0.2 microwatt.
Yeah.
So it is only 200 nanowatt power is emitted by the fluorescence, and then it is going into the spectrometer. So this is the reason that we need low light spectrometer and a cooled camera. So in that spectrometer, the camera chip is cooled to how much temperature?
Minus 80 degree.
Yeah, you can see here. Can
Yeah.
you show them, please? Yeah.
Yeah.
Minus 80
Minus
degree
80 degree it
is
is
the
cooled.
cooled, so that the noise of the CCD detector, noise floor is below, I mean is low, and then one can detect the low light. Right? So that is the idea.
And someone is asking me, can we see this fluorescence light by naked eye? So if anyone of you
Okay.
wants to check this.
And one more thing. So she
Yeah.
was saying we are claiming 200 nanowatt,
Nanowatt, yeah.
and then nobody is questioning the itna kam power. I mean, it's so low. So how are you sure about this?
Yeah.
So how can we make sure that this is 200 nanowatt? And it's a correct measurement. Any ideas from you guys? Background, very good. So how much is the background of this?
So if we close the
If we
background
close the
light,
sensor,
you can see.
0.001 microwatt, so 1 nanowatt. We are measuring 200 nanowatt with a background of 1 nanowatt. So I think it's a reasonably correct measurement. Right? Okay, what was the question?
If someone wants to see the fluorescence light, so you can check from here. Just put it here and you can see a red light on it between both of these.
थोड़ा इधर तो कैमरे में yeah.
Yeah.
We can also you will telecast live, right?
You
see
can
the
say.
nice red fluorescence?
Yeah.
Because our eyes are very sensitive. They can measure even like few photons.
So it is coming in the visible region of spectrum.
Red, red fluorescence.
Red, yeah.
Red, orange.
You show the image, no? This one.
Hold it there. Hold it there.
Zoom करना थोड़ा। और उधर देख करके स्माइल के साथ में एक फोटो लेना है इसकी।
अब तो लाइट ऑन कर सकते हैं भूपाल।
नहीं वो आएगा नहीं फ्लोरोसेंस नहीं
ओके
आएगा।
ओके ओके।
हमारी भी ले लो यार इनके साथ।
Happy faces.
Anybody wants to see come close? Yeah, जो पीछे हैं maybe they yeah.
Anybody
please.
want to see the fluorescent spot
पहले
or
पहले
the
पहले
slide?
guests को आपको बाद में आप तो यहीं हो right?
Yes, come.
Anybody from the band want to? Okay, then you can come here. Sure.
Yeah.
If guests are not interested, no issues.
Just put it here. You can see. You show the NV on the screen? No? No? Okay. To see the NV, you can see here. These all are NV. And these are the clusters of NV. This will give a good fluorescence because many NVs are collected here.
Measure it on the cluster of
No. We can get here also, but because the fluorescence signal is very low, that's why we put it on. What?
So by NVU means the vacancies?
Yeah, nitrogen vacancy center.
So what is the resolution of this camera that we can see the nitrogen vacancy clusters? Because nitrogen vacancy cluster will be on the nanometer scale, no?
Yeah, so this is also in the nanometer range, no?
No, but generally I thought this is optical camera.
Yeah, this is थोड़ा what? What?
एनवी सेंटर कौन से हैं इसमें वाइट वाले जो बैकग्राउंड
ये एनवी सेंटर हैं, ये सब दिख रहे हैं ना?
जो थोड़ा ग्रे
हाँ ये सब एनवी हैं और ये जो स्पोर्ट हमको दिख रहे हैं ये क्लस्टर्स हैं कि बहुत सारे एनवी वहाँ पे कलेक्ट हो गए हैं और यहाँ पे भी आ जाती है फ्लोरोसेंस अगर हम सिंगल एनवी पे फोकस करना चाहें, बट क्योंकि सिग्नल कितना कम था इट इज़ इन नैनो वॉट, दैट्स व्हाई वी फोकस इट ऑन ए क्लस्टर एंड वी कैन गेट ए गुड emission spectra. Yes. You want to see? So I can move it. Okay. There. It can give fluorescence anywhere.
And if we focus on individual, then it will be very less output.
Yeah. Output is very low. That's why we take the signal on cluster. तुम लोगों ने